Ciao, Physics 1. Welcome to part 1 of Wednesday's lecture on Chapter 10, Collisions. And as I recall from our first reflection assignment, this was something most of you were excited about, and I hope it doesn't disappoint. All right, so first of all, something to know about collisions is these happen all the time. Everything is bouncing into everything else. You got air molecules bopping around you right now. We've got stuff in outer space crashing into each other. And if we were in session, maybe some students would run into each other on the quad. But, I don't see that happening very much these days. So, from molecules to balls, we all run into each other. And it's really a physicist's favorite thing to do, is to crash things into other things and see what happens. I mean, that's what dark matter research is all about, and I spent a decade of my life doing that. All right, so now there's some important things to know about collisions. Objects do not need to come in contact with one another. For a collision to occur. A long-range interaction will suffice. So for example, two magnets. One magnet can repel the other magnet, and never the two ends shall meet. Two charged particles. As you'll learn about next semester, you can see that a charged particle, so if you have a stationary charge here and a minus charge coming in here, what will happen is it will go, oh my gosh. Actually, oops, there we go. Positive charge. Oh my gosh, yuck, same thing. And then, of course, gravity. So you can have a gravitational deflection and never the two objects come in contact. All right, so we have done collisions with only the momentum principle. But that really doesn't give a complete look. We are now going to bring energy to the table. EP out to play. See, when I was growing up and I had my friends, that was way before cell phones, and it was very much go over to their house, knock on their door. Can Jordan come out to play? Oh, I suspect my daughter won't know that world. And that's okay. All right, so to analyze collisions, choice of system has been important all throughout this class, and a collision really isn't an exception. So in analyzing collisions, we choose both colliding objects. To be in the system. Why do we do this? Because we can learn all we need to know and it's a lot easier. Most system choice has everything to do with, first of all, making sure that you can learn the required amount of knowledge, but also, you want to make it easy. There are no brownies for doing things the hard way that get you the same answer. Really. Okay. And the result of putting them both in the system is this makes the forces between them internal. Something else to know about collisions. Collisions are brief. And so energy flow from Q is negligible. It doesn't take very long for two things to crash into each other and then to see the effects. I mean, look at that. Bam! That was fast. All right, so the other benefit as delta T is very small, there's no time to react, or there's no time for interactions with the surroundings. If that's not the case, then you're not dealing with a collision. This is by definition. So therefore, the consequence of that is all energy and momentum are contained within the colliding objects. All right, so therefore, delta P system plus delta P surroundings is equal to 0, and I just said there's no contribution from the surroundings. So the change in momentum of the system must be 0. This is a product of the conservation of momentum applied to a collisional setup. We did see this previously. So the final momentum must be equal to the initial momentum. It also follows that the energy, the change of energy of a system plus the change in energy from the surroundings is equal to 0. Conservation of energy right there. I just told you this was 0. Therefore, the change in energy of the system is equal to 0. It can exchange between objects inside. And final energy is equal to initial energy. All right, so this is what we're going to use going forward as we analyze different systems. So, pretty cute, eh? So, okay, and if you think about it, I'm just going to give one quick example about external forces being negligible. So think about it. If you played dodgeball, and everybody should play that brutal game at least once, and you throw two dodgeballs at each other, and they hit, in that moment that they hit, so they're going to deflect and go two different directions, I assure you that the force of that collision is far greater than the mg on either one of those balls. So all the force that is worth measuring is in collision. And it's much bigger than something okay. All right, so just, and you know, you might already be saying, but wait, what about, so what about this? So yes, there are limits. There are some limits. Some limits to this approach, and we will talk about them. But this is going to work for the scenarios we're going to use it on. This will work for this chapter. And it works for things like particle colliders, where very precise measurement is very important. So there are many, many applications towards this. All right, so moving on. There are two main categories of collisions. We have elastic and inelastic. All right, so to talk about this, we need to define some parameters. So we will mostly focus on the change in translational kinetic energy, and then internal energy is generally everything else. Remember, these are short periods of time where you don't have necessarily a lot of displacement. Okay, so what is an elastic collision? The internal energy of the object does not change. In other words, they don't deform, they don't, any of that. So delta E internal is 0. No kinetic energy is converted into internal energy. So let me write that out. Delta E internal is equal to 0. No kinetic energy is converted into E internal. So therefore, this implies that K final is equal to K initial. And yes, these really do happen. So, and then just a quick reminder aside, P final is equal to P initial for all collisions. And this is because external forces are negligible. So the final kinetic energy does not necessarily equal the initial kinetic energy because it can be converted into internal energy, but final momentum always equals initial momentum. All right, so to see a perfect elastic collision, you would need to go to particle land. So perfect examples of elastic in particle collisions. And we actually saw some examples of these a little bit in chapter 8. So, for example, you have the first excited state of mercury is 4.9 eV, and a 3 eV electron collides with the Hg. All right, so in order to excite your mercury, you need exactly 4.9. And therefore, the electron is going to keep every little bit of its kinetic energy. It can't go anywhere else. So it will come in with 3 eV. It will leave with 3 eV. and ignore that angle. All right, so there is not enough energy available to change the E internal of the hydrogen, or sorry, the mercury. All right, so that is an example of a perfectly elastic collision, and these really do happen. Now, macroscopically speaking, there are no perfect elastic collisions. There's always some dissipation. Sometimes we'll take an elastic, we'll look at a macroscopic collision and say that it is elastic enough to use that assumption, but that is always sort of a rounding assumption. And sometimes it'll work well enough. You can learn enough information. So there's always some energy dissipation. If there's energy dissipation, it is not elastic. So some collisions, actually let me get this on new paper. So some examples of macroscopic collisions that are close to elastic would include things like billiard balls, so billiard balls, two springed carts, on a nearly frictionless track. All of those things we might say, okay, there's technically some energy dissipation, but compared to everything else it's negligible. We're going to treat it like it's elastic. And it's always the question of, can you measure the difference? If you can't measure the difference, then leave it the way it is. So actually, let me write this out. Question: are your instruments precise enough to measure dissipation? All right, so then it would follow, if it's not elastic, you can measure dissipation, either in terms of rounding or in reality. Then you have an inelastic. Meaning there is a change to internal energy. Okay, and so that can take the form of heat. So is it hot afterwards? Is it deformed? So throw a clay ball at a wall, you'll see deformation. Is it rotating? Is it vibrating? Etc. All right, so an inelastic collision where internal energy are not 0. So that means some K is converted to E internal. Therefore, the final kinetic energy is not equal to the initial kinetic energy. Now, remember, I'm going to write this again because it's important. This is still true. Initial momentum is still equal to final momentum. This is true for all collisions. And as I said before, macroscopic collisions are always a little bit inelastic. So the collisions that you have observed directly, all inelastic, at least a little bit. Okay, so we did a particle example for elastic. Let's do a particle example for inelastic. So now we have a 5 eV electron collides with a mercury in ground. Now we have an excited mercury, so it has 4.9 EV above ground. So that would be an internal energy change. And our colliding electron now has 0.1 EV of kinetic energy. Okay, so quick example. Now, my favorite name for a type of collision, maximally inelastic collisions, which we also call sticky collisions. These are collisions with maximum dissipation. So just a quick aside. Momentum is still conserved. So they might be moving. All right, but what often happens is they're likely stuck together. They might be stuck together. Stuck in the middle with you, here I am, sticky collision with you. All right, so all remaining K is due to conservation of momentum. So any K that can be converted is converted. Momentum conservation still holds. It always holds. And energy conservation still holds. It's just all been turned into something else. So for example, I'll draw a picture. Got two balls of clay going towards each other. They smash together, and now, so they had, there was a V1, there was a V2, now they both have V3, and they're stuck together. So, if you have to make a judgment call. So judgment call about what type of collision. So it is elastic. Objects are stuck together. That is a sticky collision, so therefore it is inelastic. Let me fix that. If the objects are deformed after the interaction. Objects measurably hotter. More vibration or rotation. Object in excited state. Basically any change in internal energy. So any of these things are measurably true. This is clearly an inelastic collision. If these things are not true, or so basically you're either in particle land or you have enough clues, and we'll do some practice of this within the problem setup, that you're going to say, okay, technically it's macroscopic, but it's virtually elastic. So therefore, we're just going to assume elastic for the sake of calculation because the contribution of the change in internal energy is barely measurable. Okay. So, moving on. Let's look at a head-on collision of equal masses. All right, so we're going to start practicing applying both the energy principle and the momentum principle to collisions. All right, so let's look at two rolling carts. And we'll do this on new paper. All right, so cart 1 with mass m moves right with momentum P1 xi, so they're both moving in x, and runs into cart 2 with mass also m, and it's at rest. Okay, let's see what we can learn about this particular situation. All right, and we're going to neglect air resistance and friction. All right, so we know the momentum principle. We know it quite well, actually. So we know that P1 x final plus P2 x final must equal P1 x initial plus 0. Because remember, it started at rest. All right, so What the momentum principle does not tell us is how it's going to be divided up between the two carts, because for that we need the energy principle. So to determine momentum distribution, we need energy principle. So we go over, we knock on their door. Can energy principle come out to play? Absolutely. All right, so before the collision, cart 1 had K1 initial, and both carts had some internal energy. So after the collision, there is still energy internal for both carts. And we now have both carts moving. K1 final plus K2 final. So both might have changed. And to go after that, we need to know more. Okay, so let's do an example where we can know more. So, cart 1 collides with at rest cart 2. These are spring carts, of which we have examples of in this lab. And they're too big for me to show you with this setup. So we can treat as elastic. So in other words, these they're going to repel. Maybe with springs, maybe with magnets. And therefore, the change in internal energy is 0. So the internal energy is there the whole time, it just doesn't change. So what is P final for both carts? So let's make this super easy. Y and Z do not change. So we can keep it scalar. In X, easy. Okay, so our system, per the convention we talked about, it's both carts. The surroundings. Earth, track, air. We are neglecting air resistance. So these are the types of carts that you typically play with in a physics lab. And so either you have an air table, which is way better, or you have these tracks that they say are frictionless. They're not. That you use to do this on, so you can pretty safely neglect air or friction. So by the way, air hockey, great example of a nearly frictionless surface. So the initial situation. just before a collision. So when you're doing collisions, you really only want to analyze just before and just after. Anything else is not really relevant. That's a different analysis. And so, of course, if you want to, include all of that, then you're looking at a computer program similar to the iterative method, and you're not doing it by hand. So just after collision. So we're going to use the momentum principle. So Px final is equal to Pxi plus F net delta T. P1 x final plus P2 x final is equal to P1 xi plus 0. All right, then we'll bring the energy principle to play. On a new sheet of paper. So the energy final is equal to the initial energy plus work plus Q. Now, nothing in the surroundings to do work. Q is negligible. We've said that at the beginning. So we have Ki final plus E internal plus K2 final plus E internal. 2, 1, is equal to K1 initial plus E internal plus K2 final plus E internal. All right, so we have said the internal energy doesn't change. So where are my zeros at? They are right here. All right, and then also this one starts at rest. So we have K1 final plus K2 final is equal to K1 initial, which is plus 0. Just a big plus sign now. And as an aside, if you recall, kinetic energy is equal to P squared over 2m. Therefore, we have P1 squared x final over 2m plus P2 squared x final over 2m. Remember, we wanted to go after that distribution of momentum. Pi squared x over 2m. Aside, as we had previously said, P1 xi is equal to P1 x final plus P2 x final. So we can use that to plug into here. And so we have P1 squared x final over 2m plus P2 squared x final over 2m is equal to P1 x final plus P2 x final. So now we just have everything in terms of x finals instead of an x initial squared divided by 2m. And so we have 2m's over everything. Divide both sides by 2m. Or sorry, everything over 2m, so multiply both sides by 2m. P1 squared x final plus P2 squared x final is equal to P1 x final squared plus 2P1 x final P2 x final plus P squared 2 x final. That would be just a foiling of this. And that leads us to P1 x final times P2 x final is equal to 0. Everything else is on both sides of the equation, so we can cancel it out. So there are two solutions. They mathematically, and only one of them works out physically. Either P1 final is equal to 0, or P2 final is equal to 0. So if P1 final is equal to 0, cart 1 comes to a complete stop. And cart 2 has all the momentum. That works out. So if P2x final is equal to 0, in that case, cart 1 goes through cart 2. Mathematically, that is fine. Physically, that's not going to happen. So therefore, not physical, only one actual solution. So remember, I said in physics, you can model things all you want. If they do not match physical reality, then your model is just a nice, pretty exercise. Perhaps it was fun, but it's not accurate. It can go to the dark places of archive. And also, you can't say that P2 final is equal to 0 and P1 final is equal to 0 because P final is equal to P initial, and P initial is not 0, as stated at the beginning of the problem. All right, so that wraps up part 1 of Wednesday's lecture. I'll see you next time for part 2.